Hi folks, we are on day 3 of the Unit 4, and in today's lesson we're going to look at strategies for evaluating limits algebraically, as well as some properties of limits that we're allowed to use. The properties are pretty straightforward, and I think that most of you guys will look at these and probably would have assumed that these things are true, but we want to kind of mathematically state the properties that we are allowed to use, for instance, being able to evaluate the individual pieces of limits and what the limits of some common functions will be. So first off, just make sure that you have somewhere in your notes the formulas for sum and difference of cubes that you would have looked at last year. In case you don't remember those, give yourself a refresher because that definitely does come up. And then we're going to take a look at, I think there's 7 different properties of limits that we will be using to evaluate the limits of more complicated functions than what you saw in the first day's homework on limits. So the first property is that the limit as x approaches a of any constant function is just that c value, that constant. And if we think graphically about what that means, to just kind of sketch this out here, remember that a constant function, so like f at x equals a constant value, think about what that would be graphically. It would just be a horizontal line. So if you have a function like f at x equals c, or y equals 3, then it doesn't matter what your x value is approaching, the y value all along that constant function will just be the value of that function. So the limit as x approaches any number of a constant is just that constant. The next one, the limit as x approaches a of just an x. So this would be the function y equals x, or f at x equals x, which is just that, like the basic line with a slope of 1 and a y-intercept of 0. So hopefully you guys can see pretty clearly from a graphical kind of picture of this, that whatever your x value is getting closer to, that would be the same as the y value, because this is a special line where all of the x and y values are the same. The next property is a little bit more abstract, but this states that the limit as x approaches a of a composition of functions that we get by adding 2 functions. So here, if we're doing f at x plus g at x or minus g at x, that we can break that apart and we can take the limit as x approaches a of f at x plus or minus the limit as x approaches a of g at x. So we can combine together the individual pieces from these functions, and this will allow us to kind of build up bigger rules for evaluating limits. So if you have the sum of 2 smaller functions, you can just take the limit of each function and add or subtract those as shown. The fourth property, if we have the limit as x approaches a of a constant value times a function, and we know the limit as x approaches a of that function, we can just multiply that limit by the constant value. So kind of a constant multiple. The limit as x approaches a of the constant multiple of some function is just that constant multiple times the limit as x approaches a of the function. Number 5 is similar to number 3. If we have a composition of functions or 2 functions combined with multiplication, then we can take the limit of each smaller function and multiply those limits together. The same for number 6 works with division, provided that the limit of the denominator is not equal to 0. And we saw in the previous lesson how oftentimes we may get a rational function and may get an indeterminate case and need to do some simplifying because we can't have that 0 in the denominator. Then the last one, again, pretty straightforward. If we have a simpler function to an exponent, if we can take the limit of the function without the exponent and get a value, and we just raise the value of the limit to that same exponent, which works obviously with the property of the multiplication function, and as exponents are just kind of repeated multiplication there. So those are all of the properties we can use, and it's going to allow us to manipulate our limits a little bit to help us be able to simplify things before we try to evaluate them. So the first strategy, if we're looking at this first example, the first strategy is one that we did look at in the previous lesson, and it's kind of like the only strategy we looked at in the previous lesson, and that was factoring. So here we have a rational function, and I like to just kind of double check. Sometimes it's obvious when you substitute in a number into the function. If we substitute it in 1/2, you may have to kind of use your calculator or do a little bit of work here to confirm that this would be that indeterminate case, that we would in fact get 0 over 0. So you could just kind of make a note like 0 over 0, it's indeterminate. Some of the easier ones yesterday were pretty obvious, like if it was just kind of an individual factor or something where x equaled 0 and we had an x factor on the top and bottom. But if you need to kind of use your calculator there to do that, that's fine. So whenever I get an indeterminate, especially if it looks like a rational polynomial expression, for my function, I am going to factor the top and bottom. The factoring strategy is probably the easiest one. So here I have difference of cubes on the top, and remember that difference of cubes is x cubed minus y cubed is x minus y, so this would be 2x here minus 1, because this is 2x all cubed. And then we've got 2x squared, so 2x times 2x is 4x squared, plus, and we'd have the cubed root of each of these things multiplied, so I get 2x, plus the second term squared, which is 1. And then I'm going to factor the bottom, whichever way you guys are used to factoring here. I'm going to assume that that's going to be 1 and 1. And I actually kind of like looking ahead, I know I'm going to want to factor that. So I'm going to try 2x and 3x, and then these would both have to be negative to make the -5 in the middle. So then I have something that can get reduced. I would have had x is not equal to 1/2 as a restriction on the function, but we don't have that restriction on the limit, because the limit, like the actual definition of a limit, is that you're not actually touching that value of x, you're just getting closer and closer to it. So we get 4x squared plus 2x plus 1 in the numerator over 3x minus 1 in the denominator. And if we sub in x equals 1/2, we're definitely not going to get that indeterminate form anymore, because I can for sure see that 1/2 would not make that equal to 0. So now I'm going to just sub this in, 4 times 1/2 squared plus 2 times 1/2 plus 1 over 3 times 1/2 minus 1. Now, notice here that I have dropped that limit notation. I was still evaluating this as a limit, but now I'm at the point where I've substituted in, so I drop that limit notation, but you have to keep it until that step where you sub in. So 4 times 1/2 squared, 1/2 squared is 1/4, times 4 is just 1, 2 times 1/2 is 1, and then 1. Over here we get 3 over 2 minus 1. So we get 3 over 1/2, which is 6. So I'm able to evaluate that limit just by factoring first. So that's our first strategy. That's probably the most straightforward one, and the one that we did see in yesterday's lesson. The factoring that you see in today's, though, may be a little bit more complex when you've got those sum or difference of cubes. The next strategy I call substitution. Some people don't use this strategy and instead just kind of factor things in sort of a much more complex way. So you don't necessarily have to use this, but it can be really helpful. So what I'm going to do is look for, and this is a little bit arbitrary, I'm going to look for the messiest piece. So I have the limit as x approaches 0 of x plus 8 to the exponent 1/3, like that's not friendly, minus 2 over x. Now, just to confirm, I would get the indeterminate limit here. So if I put in a 0 here, I'd have the cubed root of 8, which is 2 minus 2, so a 0 on top and 0 on the bottom. So this is 0 over 0, and it's indeterminate. Remember, sometimes there's tricky ones that are actually quite easy because you can sub in and it's not indeterminate, but people sometimes assume that they're going to have to simplify and go through a ton of work when you may not have to. So always double check that it is in fact indeterminate before you do more work like this. So I'm going to look for the thing that I really want to get rid of, basically, okay? And this thing here is the thing I really want to get rid of. Like that x plus 8 to the 1/3, I don't know how to factor that. Well, I do, but you maybe don't know how to factor that, and you probably have not seen that before. So I'm going to say I want to get rid of this x plus 8 to the exponent 1/3. That's a mess, and I want to not have it in my equation. So I'm going to substitute that with a u. And I'm going to leave out part of this right now. I'm not putting what the limit is. I'm going to instead say u minus 2 is now on top. Okay, so I have to state what I'm doing. I'm going to say let u equal x plus 8 to the exponent 1/3. Okay, so that made my numerator much better. U minus 2 I can cope with, but I still have an x in the bottom. So what I need to do is figure out what x equals. So I'm going to go to this relationship that I've defined and figure out what will x equal. So I have to solve for x. So I could say that u cubed equals x plus 8, and then x equals u cubed minus 8. So that's okay. That's still not terrible, right? I don't have that bad cubed root situation happening anymore. So I'm going to take this in and sub it in up here for that x. Well, I'm going to in the next line, of course. Okay, so then I've got u cubed minus 8. This looks a lot better. Okay, it feels like something that I can deal with. The other situation is here. I had the limit as x approached 0, but I don't have any x's in my equation. I have to figure out what u would be doing as x approaches 0. So as x approaches 0, remember u is x plus 8 to the exponent 1/3. So u is approaching 0 plus 8 to the exponent 1/3. U is approaching 8 to the 1/3, so u is approaching 2. Okay, so that I'm going to have to sub back in as what my variable is approaching in my limit, because I can't have a limit of an expression with u's and say what's happening as x approaches 0. I have to figure out what my corresponding variable would be doing. So I'm going to say as u approaches 2. Now this is still indeterminate. I've got 2 minus 2 on the top and 2 cubed minus 8 on the bottom, but it's much easier to deal with now. And now we see we're back to our factoring strategy. So I have a difference of cubes on the bottom. So the limit as u approaches 2 of u minus 2 over u, minus 2 times u squared plus 2u plus 4. So now I have something that is much easier to cope with. So the limit as u approaches 2 of 1 over u squared plus 2u plus 4. Now I'm ready to sub in, because now if I put in a 2 here, I'm not going to get the indeterminate form. So when I'm ready to sub in, then I drop that limit notation. I just have equals 1 over 2 squared plus 2 times 2 plus 4, which is 1 over 12, 4 and 4 and 4 on the bottom. Okay, so this is probably one of the most complicated things, but this technique, you just have to remember, pick the messy, terrible thing that you want to get rid of and make it equal to a variable like u. Then you're going to need to figure out what x is in terms of that other variable, because there's typically somewhere else to plug in. And you also have to figure out what's that variable getting close to as x gets close to the number that was in the original limit. You sub those things all out and you come up with something much easier to simplify. Oh, this is the same one. I thought I maybe would need more space to do that. And the last strategy is multiplying by the conjugate. So here, the limit as x approaches 0 of x plus 5, root x plus 5 minus root 5 over x. We can see obviously a 0 in the denominator. Here we'd have root 5 minus root 5. So this is, in fact, indeterminate, with a 0 over 0 limit. So the strategy here is if you see radicals or square root signs, you can multiply by the conjugate. Remember, the conjugate means if you had, say, the square root of a plus the square root of b, the conjugate of that is the same square roots, but the opposite sign in the middle. So one's a plus and one's a minus. Otherwise the exact same two radical terms. And that will eliminate the square root signs by doing a difference of squares. So I'm going to take this strategy here, and we obviously, because we have a fraction, we can do this, that I'll multiply by that conjugate on the top and bottom. So I have the limit as x approaches 0 of root x plus 5. Oops, extra brackets that I didn't need there, minus root 5 over x. And then I'm going to multiply this by root x plus 5 plus root 5 on the top and bottom. So I get the limit as x approaches 0. Now on the denominator, I'm not going to simplify this. I'm just going to say that that's x times root x plus 5 plus root 5. And then on the numerator, I'm going to distribute this out. So here I'll get root x plus 5 times root x plus 5, which is just x plus 5. Then here, this is where we'd be like foiling and we have a difference of squares. So I'd have these two multiplied with a positive, then the same two terms multiplied with a negative. So they would cancel each other out. Then I'll have minus root 5 squared, which is just 5. So minus 5. Okay. Simplifying and cleaning up a bit, we've got the limit as x approaches 0. And now on the top, x plus 5 minus 5 is just x. And I also had that factor of an x on the bottom. So those will reduce. Am I going off the screen here? The limit as x approaches 0 of 1 over root x plus 5 plus root 5. Here is the point where you could drop the limit notation because I'm going to sub in a 0. So I just have equals 1 over root 0 plus 5 plus root 5. So I have 1 over 2 root 5. Rationalizing this denominator here for proper form. I think that some in the textbook, I believe some don't rationalize the denominator for the answer. But it's always good form to do that. So here we've got root 5 times root 5 is 5 times a 2 as well. So we have root 5 over 10. So that's it. Those are the 3 main strategies that you guys are going to be using to be able to simplify limits that are in an indeterminate form in order to be able to evaluate them.